Swayam Prabha. Digital India. Educated India.
Alright, so now we have taken a look at Boolean algebra, which is the manipulation of bits. We have taken a look at how positive integers are represented in binary, how negative integers are represented in binary. So let me maybe just summarize at this point. So we have, for a quick recap, Boolean algebra had to do with Boolean variables, where each variable could take a number between, sorry, not between, a number which is either 0 or 1, and we defined basic operations on Boolean variables, such as the AND operation, which means that the AND function is true only when both the variables or all the variables involved in the AND operation, all of them are 1, and the OR operation is correct only when is true only when one of the variables is 1. Then we define a NOT operation, that's a complement, and we define an XOR operation, which is 1 when one is 0 and the other is 1. Then we define the binary system to represent positive integers with different bases. So the important point to recapitulate, for at this point of the lecture is that what is the relationship between binary, between octal, which is base 8, and between hex, which is hexadecimal, which is base 16. And the important result that we had proved is that the octal and hexadecimal notations can be thought as short forms, abbreviations or reduced representations of a binary representation. So what do we do? For example, in base 16, we just group blocks of 4 binary numbers and represent them with one base 16 number. For example, a number of this form, right, which it can be represented as, this becomes 1, and this is actually 8 plus 3, 11, which is B, right? So instead of having 8 digits, we only have 2 digits. Then we represented negative integers. We looked at different methods of representation. One is the sign magnitude representation, which has a sign bit. The problem there was that performing arithmetic operations was difficult, and there were 2 representations for 0. The other was ones complement, same problems, 2 representations. The other was with a bias. So with a bias, we had a single representation for every number, but even addition and subtraction were relatively easier, but multiplication was hard. So that's the reason we introduced 2's complement, where essentially the 2's complement of a positive number is a number itself, and a 2's complement of a negative number is 2 to the power n minus u. The fantastic thing about this number system is, yes, it preserves the notion of the sign bit. It's easy to find if a number is positive or negative. Just take a look at the MSB. There is one representation for 0 and all other numbers. And performing addition, subtraction, and multiplication is simply as simple as take the unsigned representations of the numbers and add, subtract, and multiply them. The last n bits of the result are the representation of the last n bits of the result are actually the representation of what the actual result should have been, right? And similarly, so then we discussed some properties of this number system, which is what are the conditions for an overflow. That's very important. And we also discussed the issues of sign extension, which is that when you convert a number from from an n-bit system to an m-bit system where m is greater than n, what do you need to do? Now let's discuss floating point numbers, which are numbers with a decimal point. So what is a floating point number? Is any number with a decimal point inside it, like 2.356 or 1.3 times 10 to the power minus 10. So now the question is, the moment we say that a number is a floating point number, we need to answer the question, what is a fixed point number? So if in a fixed point number, the number of digits after the decimal point is fixed. So one example of such a number is 3.29. So any number representing, let's say, currency is a fixed point number. So the number of digits after the decimal point is fixed. So what is the generic form of a number in base 10 if we consider just positive numbers? If we just consider positive numbers, the generic form of a number in base 10 is 3 times 10 to the power 0, which is 3, plus, 0.2, which is 2 times 10 to the power minus 1, plus 0.09, which is 9 times 10 to the power minus 2. So any generic form is a form of this type where we make a summation from a minus n to a plus m or plus n, where we are essentially adding powers of 10 with a coefficient. So in this case, the coefficient is 2 and 9 and 3 and so on. So what would a generic form of a number be in base 2? All that we can do is that we can take 10 and replace it with 2. So let's take some simple numbers and expand them in this notation. So let's say 0.375 is 2 to the power minus 2 plus 2 to the power minus 3. A number like 1.5 is 2 to the power 0 plus 2 to the power minus 1. A number of the form 17.625 is this representation as shown over here. 2 to the power 4 plus 2 to the power 0 plus 2 to the power minus 1 plus 2 to the power minus 3. So if we can use base 10 to represent all floating point numbers, right, all decimal numbers, like the value of pi and e and even a number like 5.36 times 10 to the power minus 17, nothing stops us mathematically to replace base 10 by base 2. So what do? We take the base 2 representation of a floating point number. So what we have done here is that we have replaced replaced base 10 by base 2 everywhere. Just one small correction here. This should have actually been minus 3. So we have replaced base 2 by base 10 everywhere. And so as I said, if you go to a planet where people have only 2 fingers, they would use base 2, they would not use base 10. And pretty much any base 10 number has an equivalent base 2 expression, which is an expression of this form, which is just a binary representation of the number from base 10 to base 2. And so if you consider 10.11, in decimal this would be 2 plus zero point 0.1 is 2 to the power minus 1, which is 0.5, plus 0.25, which is 2 plus 0.75 or 2.75. So this gives us a very easy way to at least represent positive numbers with, by just simply extending the logic and instead of base 10 using base 2. So let us now create a standard form of all floating point numbers. So in this case, we'll use the sign magnitude representation because otherwise it will become too complicated. So any number a can be represented as minus 1 to the power s, where s is the sign bit. If s is 0, then minus 1 to the power s is 1. And if s is plus 1, which means the number is negative, minus 1 to the power 1 is minus 1. So the number becomes negative. Then we can define p, which is the significand. So the significand is typically a number between 1 and 2. In this case, not typically, it is a number between 1 and 2. So we can represent the significand as a number as 1 plus m, where 0 is less than equal to m and m is less than 1, multiplied by 2 to the power x, where x is an integer, right? So x is an element of z, which is the set of integers. And it's a significant, so let's just go over this terminology once again, it's very important. So any floating point number we're representing as -1 to the power s, where s is the sign bit, multiplied by the significand. The significand is a number of the form 1 plus m, where m is strictly less than 1 and it's positive. M is called the mantissa, right? So the m is given a name, and the name of the number, the name of this term is the mantissa. Multiplied by 2 to the power x, where x is the exponent and x is an integer. So as we see, any number can be represented in this form. There's absolutely no problem. Like a number of the form 2.6 can be represented as -1 to the power 0 multiplied by 1.3 multiplied by 2 to the power 1, where 1.3 is the significant, which is 1 plus 0.3, where 0.3 is the mantissa. So this is also called the normal form or the normalized form. So let's see some examples, at least in decimal. We'll go to binary later. So 1.387 times 10 to the power minus 23. So the significand is 1.3827, mantissa is 0.3827. Since we consider in decimal, instead of base 2 it's base 10, so the exponent is minus 23 and the sign bit is 0. Similarly, 1.2 times 10 to the power 5, the significand is 1.2, mantissa is 0.2, the sign bit is 1, which means it's -1 to the power 1 at the leftmost point, and the exponent is +5. So let's now take a look at the IEEE 754 format for representing floating point numbers and take a look at the general principles. So the significand should be of the form 1 point something. So there, see, if you think about it, if we have 32 bits, so this is a 32-bit number system. If we think about it, if every number significand is 1 point something, right? There is no need to waste 1 bit representing that 1. We can assume it as the default, that it's always there. We just need to save the mantissa bits, right? For example, if a number is 1.384, we just need to save 384, right? Need a binary representation for 384. We can automatically assume that 1 is inside, is in there. We also need to store the sign bit s and the exponent x. So the IEEE 754 format is something like this. It's a 32-bit format. The MSB is for the sign bit, where we use 1 bit for the sign bit. We use 8 bits for the exponent, which means it can take 256 values. And we use 23 bits for the mantissa. So let's now take a look at the representation of the exponent. So the exponent uses the biased representation in the sense that if the exponent is equal to x, then we actually save x plus the bias. So in this case, it allows us to represent negative exponents as well. So we can actually represent exponents in the range of -127 to +128. Right? So since the bias is 127, what we actually save in this case is 0 till 255, which is a total of 256 numbers. So what was the need for having a biased representation over here? Well, the need was that the exponent can be positive or the exponent can be negative. Hence, we need to have some kind of a representation. 2's complement was found to be a bit too complicated, and it was also not required. Because typically in floating point numbers, we don't multiply the exponent by some other number. Most of the time, we only add and subtract the exponents. In that case, it was not necessary to go for something as heavyweight as 2's complement. The biased representation was found to be nice and simple. So as I said, so let's consider some examples. The exponent is 0. We actually save 127. If the exponent is minus 23, we save minus 23 plus 127, which is 104. Last example, if the exponent is plus 30, we save 157. So what are the different fields once again? The 1 bit sign bit is there. After that, we have 8 bits. And the 8 bits are for the exponent. But the exponent is actually x, its representation is e. And what is the relationship between e and x? We are saving e, where e is equal to x plus the bias. So whatever is the real exponent, we add 127 to it. And we save it in this particular number system. Now let's consider normal floating point numbers in the IEEE 754 format. So IEEE, by the way, is an association of electrical and electronics engineers. So IEEE typically makes standards and formats for representing a variety of information. In this case, the 754 format has been made, 754 standard has been made to represent floating point numbers in binary. So normal binary numbers have an exponent between minus 126 and plus 127. So the other exponents which can be represented, minus 127 and plus 128, are reserved for special purposes, so which we will discuss later. So now the standard form or the normal form of an floating point number in IEEE 754 format is exactly what we had seen before, and with a little bit of modification. So we have the sign bit minus 1 to the power s multiplied with the significand, where the significand is of the form 1 plus m, m being the mantissa strictly less than 1, multiplied by 2 to the power e minus bias, where e is the representation of the exponent. So e is between 1 and 254, right? So the values of 0 and 255 are reserved for special purposes. So here is a food for thought. What is the largest positive normal floating point number? What is the smallest negative normal floating point number? I will not answer them, but I have kept them as exercises for the reader, and the answers are in the book. So let's now take a look at some of the special values for the floating point numbers. So in this case, if you would recall, the valid values of e actually has to be in the range of 1 and 254, right? So the values that we are excluding are 0 and 255, which basically means that exponents with a value of minus 127 or plus 128 are not allowed. So if they are not allowed, what does it mean? It means that we are using these values for denoting something special. Alright, so what should it be? What it should be is something like this, that if e is equal to 255 and the mantissa is 0, let us treat this number as positive infinity, plus infinity, if the sign bit is 0. If e is 255, the mantissa is 0, and and if the sign bit is 1, let's treat this number as minus infinity. So let's give an example. 1 divided by 0 is plus infinity, and minus 1 divided by 0 is negative infinity, and infinity is represented with the fact that e is 255 and m is 0. Now let's consider the third case, where e is 255 and m is not equal to 0. So there can be many such values, but we say that all of these values represent a nan, where a nan is a not a number. For example, what is 0 by 0? 0 by 0 is undefined. So we treat this case as a nan. Or what is log of minus 1? Log of minus 1 is undefined. So let's again treat it as a nan, or a sine inverse of 5, a sine inverse of 10. It is undefined, so we treat this as a nan. Any arithmetic expression that has a nan will always evaluate to nan. So nan plus nan is equal to nan, nan minus nan is equal to nan, nan plus any other number is equal to nan. So the moment any part of an expression evaluates to not a number, the entire expression will evaluate to not a number. So in this, in the IEEE format, we sadly have two representations for 0, which is not desirable, but this is still there. So in this case, if E is equal to 0, which is one of the special cases that we had excluded, if E is 0 and the mantissa is 0, then the value is 0. So of course there are two representations. The sign bit can either be 0 or the sign bit can be 1. We thus have two representations for 0 in this particular number system, which is not something that we can, which is not much that we can do. So the sign bit can be 0 or 1, but then the E field has to be all zeros to represent a 0, and the mantissa field also has to be all zeros. And the sign bit can either be 0 and 1, it doesn't matter. It will still be, both the variants will be treated as a 0. The last subclass is very interesting. It's called a denormal number. So we will discuss this in later slides. In this case, E is equal to 0, but M is not equal to 0. So we will discuss this case in the next few slides. So but before going to denormal numbers, I just wanted to give an example of how we would represent a floating point number. So let's maybe consider a number of the form minus 1 point. No, let's consider a number of the form minus 3. So minus 3, the first thing would be to reduce it to standard form, right, or a normal form, which is minus 1 to the power 1 multiplied with 1.5 multiplied with 2 to the power 1. So this is equal to minus 1 to the power 1 multiplied with 1 plus 0.5, where 0.5 is the mantissa, multiplied with 2 to the power 128 minus 127, where 127 is the bias. So now if I consider the representation of this number in binary, then the sign bit will be equal to 1 because the number is negative. The exponent, right, the E field will actually be equal to plus 128 because we are subtracting the bias minus 127 to get 1. So this is E minus bias, right, where 127 is the bias. So E is plus 128. So let us have the binary representation of 128, and the binary representation of that would essentially be 1 and 7 zeros. Now let's come to the mantissa. So the mantissa part is 0.5. So 0.5, if we want to represent, the way that we would represent, so essentially if 0.5 is basically equal to 1 times 2 to the power minus 1. The mantissa contains 23 bits, right? So it's a 23-bit mantissa. The first bit corresponds to 2 to the power minus 1. The last bit corresponds to 2 to the power minus 23. And the ith bit corresponds to 2 to the power minus I. So the mantissa can be thought as a summation from I is equal to 1 to 23, a coefficient xi multiplied by 2 to the power minus I. Since this is 0.5, which is 2 to the power minus 1, we'll have 1 over here, which is the MSP position, and the rest all will be zeros. So this is how we would represent a number of the type minus 3 in the IEEE 754 format. Alright? And so it's actually very easy. The first we represent the sign bit. Then we figure out the value of the E field by adding the bias to the exponent, which is 128. And then we figure out the mantissa. So the mantissa, mind you, is strictly less than 1, and it is greater than or equal to 0. And it's essentially a summation from 2 to the power minus 1 till 2 to the power minus 23, each term multiplied by a coefficient. In this case, we just need to stop at 0.5. So the MSP needs to be 1 because it's 2 to the power minus 1, and rest all the terms need to be equal to 0. Right? So this is the representation of our floating point number in binary. Given this, let's take a look at some of the queer aspects of floating point math. So the smallest normal floating point number that we can have, right, the smallest normal positive floating point number that we can have is, let's work it out. So basically, since it's positive, the sign bit is 0, and the smallest value of E that we can have is actually 1. So basically, this is minus 126. This is the exponent, and the smallest mantissa that we can have in a positive setting is all zeros. So assume that f is one such number, which is the smallest normal floating point number. So we have a floating point f is 2 to the power minus 126. We take another number g, which is f divided by 2. So this number is 2 to the power minus 127, which is g, and g can clearly not be represented in our system of normal numbers because we don't have a representation for it. Now let's consider the next statement, if g is equal to 0. So now the question is that what is the value of g? If g is equal to 0, let's print error. And should this code print error, and do you think this is the right behavior? Well, intuitively no, right? So let me maybe write a big no over here. Intuitively no, because f is a positive number. G is the same positive number divided by 2. It is not equal to 0. So there is as such no reason of concluding that g is equal to 0 and printing error. But we also don't have a representation for g. So we somehow need to solve this situation. So what we can do is that we can define a set of denormal numbers where the E field in the representation is 0 and the M field is not equal to 0. And so the normal form of a denormal number, here we change the significand. Instead of assuming that the significand is of the form 1 plus M, we assume it is 0 plus M, right? 0 becomes the default and mantissa remains the same between 0 and 1. And the exponent we assume is 2 to the power minus 126, right? So in this case, E is equal to 0 and we assume that x is equal to minus 126. Mind you, it is not minus 127. This is a common mistake that students typically make. It is not minus 127, it is minus 126. So and a common question that instructors typically ask is why minus 126? So let's try to understand what's happening. So let's consider the number line and let's assume that these are all the floating point numbers that we can represent. So the smallest normal floating point number is 2 to the power minus 126, right? So basically we want to define a very small region of numbers after this, such that, so mind you, the diagram is not drawn to scale, so this part is normal, right? So we want to define a very small region of numbers around here called denormal, such that our programs make sense and this particular program does not print error. To actually ensure that this is the case, we define a normal form of this type where the significand is assumed to be 0. So in this case, let's find out what is the value of the largest possible mantissa. The value of the largest possible mantissa is pretty much equal to the mantissa or the significand, so they are actually the same, is equal to 2 to the power I, where I is pretty much, or I would say minus I, where I is going from 1 to 23, right, which is equal to 2 to the power minus 1 plus 2 to the power minus 2 all the way till 2 to the power minus 23. So this is a simple geometric series summation. And so when we look at any kind of a geometric series summation, so we can expand the geometric series and we can do some maths. I'll write down the result directly, and the result is 1 minus 2 to the power minus 23. So this is an important result, and this will come many times in the book and in our discussion. So users might want to memorize this, readers might want to memorize this. But the important point over here, if I want to find the largest denormal number, this is essentially equal to 1 minus 2 to the power minus 23 multiplied with minus 126, which is 2 to the power minus 126 minus 2 to the power minus 149. Right, so this is the largest denormal number. So pretty much if we take the number line, right, and if this point is 0, so the largest denormal number is at this point, and the smallest normal number is at this point, right? So as we see, the difference between them is really small, 2 to the power minus 149. And so some difference needs to be there, because this is after all a discrete number system. It's not a continuous number system. But the important point to appreciate is that this should not have been minus 127. It should be minus 126, because that is only when we get this property over here that we have a very, very small distance between the largest denormal number and the smallest positive normal number. And so what is the smallest, so what is the range of the denormal numbers? The range of the denormal numbers, the smallest positive denormal number would pretty much have the mantissa, the last 23rd bit would be equal to 1. So it will be minus 2 to the power minus 23 multiplied with 2 to the power minus 126, which is 2 to the power minus 149. So just to summarize, what has happened is that we have the set of all the normal numbers. We have just created a little bit more room of denormal numbers, such that a lot of our maths and our programming actually makes sense, and we don't come up with very non-intuitive answers. So that's the reason denormal numbers have been defined in this particular fashion. And so I would request the readers to take a look at the normal form for both normal, standard or normal form for both the normal floating point numbers as well as the denormal floating point numbers. Find out what are the differences, do some of the math that I did just now, and convince themselves of the utility of denormal numbers and how they can help avoid non-intuitive results. So we had pretty much the same thing in the slides, but I have overwritten them. So, but here is the, in the example, the ranges of denormal numbers, which we just found out. So the positive denormal numbers start from 2 to the power minus 149 to 2 to the power minus 126 minus 2 to the power minus 149. And the normal numbers then start from 2 to the power minus 126. Similarly, for negative denormal numbers, the range is minus 2 to the power minus 149 to the same thing, albeit with a sign reversal. So as I said, all that the normal numbers do is they extend the range of floating point numbers a little bit. And mind you, such diagrams are never drawn to scale, such that again our maths make sense. So what we saw is that the range of floating point numbers. So let's look at the range of the number systems. So for an integer with a 32-bit, so typically an integer is 32 bits, right? And that's what an int in C or in Java would typically correspond to. In a 32-bit number system with 2's complement, roughly the largest number that you can represent is 2 to the power 31, right? So maybe let me write it down that for a for a 32-bit integer, these are just rough figures. The maximum that we can go to is like plus minus 2 to the power 31. For a 32-bit floating point number, the maximum that we can go to is roughly, in the range of plus minus 2 to the power positive 127. But then, of course, the mantissa can be higher. So I can make it 128. That's maybe, the largest that we can go to. Very approximate figures. And 2 to the power 128 is around 10 to the power 40, right? Typical numbers. The approximate range of doubles is much more a double precision number because this uses 64 bits and doesn't use 32 bits. So in this case, we have a 1-bit sign bit. We have 11 bits for the E field, mind you, not 8 bits, but 11 bits. So this means that, so the bias is also different. Instead of a bias of 127, the bias is 1023, right? And we can we can cover a much larger range of numbers from minus 1023 till plus 1023. And so the range is typically plus or minus 10 to the power 308, which is a fairly large range, and we would typically not need more than this for most of our calculations. So this is a lot, right? And we don't typically need more than this. So I can add a note over here that for a 64-bit double precision, what we have double in C, we are roughly at plus or minus 2 to the power 1023, and this is roughly 10 to the power 300, right? So this is roughly 10 to the power 300. This is roughly 10 to the power 37 or 38, and this is much smaller. So 2 to the power 30 is around a billion. So this is roughly 10 to the power uh, is actually 3-4 billion, something like that. And so this is roughly a 10 to the power 9 kind of figure, slightly more than that. So it's several billion is the limit. Around 4 billion is the limit, and if I can say it's around 2 billion to be precise, plus minus. Let us now take a look at some basic floating point math that we want to add. We have two numbers, a and b, where a is 2 to the power 50 and b is 2 to the power 10. We want to add a plus b, and then we want to subtract a, but a plus b we want to be done first. That's the reason it's there inside a bracket. So if we add a and b, we are essentially adding 2 raised to the power 50 plus 2 raised to the power 10. If we do this, the result would look something like this, that the sign bit will be 0. The exponent has to be the larger one, can't be the smaller one, so 2 to the power 50, plus the significant has to be something of the form 1 plus 2 to the power minus 40, right? So this is the only way that we'll be able to represent such a number. So the mantissa has to be 2 to the power minus 40, but the smallest value of the mantissa that we can possibly represent in our system is 2 to the power minus 23, right? So this is the smallest value that we can represent. As a result, this number cannot be represented in our system. So this is a problem. So what most hardwares would do is that they will actually take 2 to the power 50 plus 2 to the power 10, and since the mantissa cannot be represented, they'll just produce 2 to the power 50 as a result. And then when we subtract 2 to the power 50 minus 2 to the power 50, C will be computed to be 0. So this is a non-intuitive result mathematically, right? So mathematically we don't expect this result. What do we expect? We expect A and A to be cancelled and the result to be B, which is 2 to the power 10. So what a lot of smart compilers can possibly do is reorder the operations to increase precision. And in this case actually break down the bracket. But this is again not what the programmer wants. So as a result, there is a big gray area over here. But the most important thing that we need to understand is that floating point math is approximate. It's not, exact. The reason it is approximate is because we have a limited number of bits, and with those limited number of bits we can and also with a lot of constraints, we can only represent a very limited set of numbers within our constraints. In this case, we cannot represent a number of the form 2 raised to the power 50 plus 2 raised to the power 10. It's simply not possible for us to represent a number of this kind. As a result, here we'll have a non-intuitive result coming at the end where C will be computed to be 0. At least most compilers would do that. A lot of compilers might want to reorder the operations or locally resolve the operations. But it is very much conceivable that this program on a lot of programming languages and hardware would actually produce 2 raised to the power 10. Would actually produce 0. It would not produce 2 raised to the power 10, which is a non-intuitive result. So programmers need to keep these things in mind while writing programs with floating point numbers, and always keep in mind that it's an inexact approximate representation. Now let's take a look at the fifth and last part of this chapter, which is representing strings. What is a string? It's a piece of text, right? In any piece of text, the same way that these slides are there where I've written ASCII is American Standard Code. This is a piece of text. How should we represent it? So the most common way of representing pieces of text was with the ASCII format. And ASCII is American Standard Code for Information Interchange. It has 128 characters. The first 32 characters are actually non-printing characters. They are for control operations, like character number 8 is for backspace to actually delete a character. Character 10 is line feed, which used to tell printers to jump to the next line. 27 is the escape character. It corresponds to the escape key on our keyboards. And then the remaining are letters, small letters, capital letters, special characters like exclamation mark and at, and numbers, of course. So since there are 128 characters, each character is encoded using 7 bits. So the ASCII character set looks like this. So here is a code of some of the common characters. From small a to small z, the code goes from 97 till 122. Similarly, from capital A to capital Z, the code goes from 65 till 90. Right, so basically then we have a numbers from 0 to 9 where the codes are assigned from 48 to 57, and there are different kinds of code for different kinds of special characters and punctuation marks that we use, like exclamation, hash, dollar, brackets, comma, semicolon, and so on. So the problem with the ASCII set is first is only for English, and English is a very simple language. In English, the number of characters are few, and we don't have special marks and what is there in other specialized characters that come up in other languages with also combinations and so on. So for this we have the Unicode format. So it's the universal character set transformation format is the UTF format. So the UTF-8 standard encodes around 1 million characters defined in this set, and it can use 1 to 6 bytes for this purpose. So what I have done over here is that I have written a couple of characters in different languages. Some of these, so this is Hindi, for example, the Devanagari script. This I believe is a Tamil character. This I don't recall. It might be a Korean character. And this is a, I think, a character from the Kannada language. So with so many characters, it is necessary to encode them. So for this, the UTF or the Unicode format was designed, which has become the standard now. So UTF-8 is compatible with ASCII in the sense that the first 128 characters in UTF-8 correspond to the ASCII characters. So when you use ASCII characters, UTF-8 will require just 1 byte. And it will have a leading 0, which means that the remaining 7 bits specify ASCII characters. Most of the other languages that use variants of the Roman script, such as French, German, and Spanish, require 2 bytes per character in UTF-8. Greek, Russian, Hebrew, and Arabic also require 2 bytes. So this has become a standard across all browsers and operating systems. So nowadays it is very common for users to read articles which have been written in multiple languages, or maybe an ad is coming in some other language. So all of this happens courtesy Unicode. So UTF-8 has been superseded by UTF-16 and 32. So UTF-16 uses 2 byte or 4 byte encodings, and Java and Windows support UTF-16. So as of now, at least UTF-16 is the more popular character set. And UTF-32 uses 4 bytes for every character, and it's rarely used. It's not that commonly used. But UTF-8 and UTF-16 are the encodings of choice, where basically every character is represented with a certain sequence of bits. And in any document, you just have character by character, which is essentially a sequence of bits that encode each character. And so when the document needs to be shown on the screen, your word processor program extracts all the bytes out, converts them into characters. For each character, it draws a small image that corresponds to the way the character should look on the screen. Alright, so this brings us to the end of chapter 2. So what have we achieved in chapter 2? Let's go back to the outline slide. So in the outline slide, we have basically shown what is possible to do with a set of bits. So we can work on them, we can define an algebra, and we can have basic operations. We can represent both positive as well as negative integers using a set of bits. So they have their constraints, but again, we overcame all of those constraints and we came up with the 2's complement notation, which is the most effective notation as of now to represent negative integers. After that, we extended the results that we had to represent floating point numbers. So in that case, we needed to go for a slightly different representation. The reason being that we actually needed to represent the exponent as well, and we also made a trade-off for simplicity. This is one of the vital learnings that you need to have, that in computer architecture sometimes you need to walk a step back and make things simple. So in this case, instead of going for a 2's complement representation of the exponent, we actually used a bias based representation, and we also used an explicit sign bit just to make our life easy, and also to leverage the pattern that you typically don't multiply the exponent. You would only multiply it when a number is being raised to the power of some other number, but that's a relatively rare operation. Most of the time we are only adding and multiplying floating point numbers. In that case, we do not per se multiply the exponent. Lastly, we talked about strings. We talked about the basic simple ASCII format for English. We also talked about the generic Unicode formats or the UTF formats. Two of them are very common, UTF-8 and UTF-16. UTF-8 and 16 are used to represent almost all the text today in all the world's languages. And they have many additional characters as well and many cartoon-like characters that can be used to make really expressive documents. So now that we have a certain hold on bits and how they can be used, we need to design a language, a simple low-level language that can communicate with the processor using these bits to accomplish fairly complex tasks, which is the main goal of the next chapter, the chapter on assembly language, to achieve complicated tasks using simple bits. So see you then with chapter 3, which is going to be the next lecture.